From the beautiful studios of Way Happy, this is Mr. Meyer and Section 4.1 angles and their measures. All right, so you guys have been doing degrees, and from degrees, from geometry, we know that a straight line is 180 degrees. So I'm going to use that logic right now, and I'm going to say, all right, here's a straight line, and that's 180 degrees, right? And this is 0 degrees. We call that standard form. Now let's drop in a right angle. Remember, a right angle is 90 degrees, which means that if you do 90 plus 90, you get 180. If you add another 90, you get 270. And if you go all the way around, you go all the way around. It's called 360 degrees. Now that is all fine and good and really helpful if you remember that. In fact, it's really helpful if you can remember some things like there's a 30-degree angle and there's a 45-degree angle. These were special right triangles from geometry. Or a 60-degree angle. Those are super important to know. And you want to know those all the way around this circle. Now, degrees are great and all, and they can be measured. Like you can make degrees a little more precise, right? The way you do that is 1 degree is 60 minutes. So believe it or not, you have 1 degree. You could break it up into 60 parts called 60 minutes. You can break each minute up into 60 seconds. So imagine how tiny you can get, and your calculator can actually do this. Your calculator has a little button and it has a little arrow and it says degrees, minutes, and seconds. So if you ever see this DMS notation, that's your calculator's way of saying degrees, minutes, and seconds. So we can convert to degrees, minutes, and seconds, and we can convert out of there. It's called stoichiometry or dimensional analysis, and I think I have one later on in this video. All right, 1 revolution around a circle we know is 1 rotation around the circle, and that's 360 degrees. Now, the bad news about degrees, are you ready? We all know them, we all understand them, we all get them, we think they're great. They're worthless. They're absolutely worthless. These are no good. You know why? Because they have no mathematical background. They have nothing to do. Why pick 360? Why not pick 400 and make each quadrant 100? Or why not make everything, make a whole revolution 10, right? And then half a revolution's 5 or something like that. I don't know. Pick any number you want. If it actually had a mathematical value to it, then, if it actually made sense where we could use it, then it would be worth something, but it doesn't. In fact, the only thing I think I've ever heard it come close to is 1 rotation around the sun is 365 days. So back in the ancient, before then, they thought of a complete circle as 360 degrees because it took 360 days to revolve around the sun. I don't know if that's true or that's somebody just trying to make something up. No idea. All right, what about this other way called radians? Now, doesn't mean I won't use degrees. I will use degrees because everyone knows degrees. My daughter is in middle school, and if I tell her 45 degrees, she knows what it is. My elementary school kid knows what 90 degrees is, so it works, right? But math geeks would be rather using something a little more helpful. And we know that circumference of a circle is 2 pi r. Well, what if I change the radius to be 1? Then circumference is 2 pi. And somebody said, all right, well then all the way around should be 2 pi, which means that halfway around would only be 1 pi. And means, if you went halfway, what we'd call 90 degrees, that would be half a pi, or what most people like to write as pi over 2. And so, I should get that 270 down there, right? That's 1.5 pi's, so this would be 3 pi over 2. And there you have your way around the units, or around the circle, using radians. Now, radians are super important, super fancy, and super awesome. Now, they actually come from somewhere, the circumference of a circle. And the circumference of a circle wasn't made up either, and pi wasn't made up. People actually measured the circumference, and then they measured the diameter, and they divided it, and they got pi every time. And that's where people started to realize it didn't matter how big or small your circle was, that the relationship between measuring the outside of the circle and the diameter, there was this constant relationship, which we know as circumference is 2 pi r, or pi d if you want to use diameter. So, that's a lot of information. But let's talk about this. What can we talk about? Standard position, probably the most important. Standard position is when you draw an angle starting at 0 degrees or 0 radians, right? So you start your angle at, let's say I'm going to do it over here in the radians. Right here, that is 0 radians. and you have what's called the initial side. That's where you would start it, the initial side. And then you're going to go to what we call the terminal side. And there's always a kid in class that's going to ask me what the terminal side means. And you're going to see smoke come out of my ears, because I feel like you should know that terminal sides mean where's that angle end. You're going to start measuring it up this way. This is the positive measuring direction. And so you're going to go like 1 radian, 2 radian, whatever, right? And then you're going to come out and you're going to stop. And wherever you stop, that is called our terminal side. Terminal, right? That's where we ended. The initial side was the one you started with. And in standard position, initial side's always at 0. So you got initial side, terminal side, standard position. Okay, got it. Measuring, if I go measuring what we call counterclockwise, moving the way a clock does not move. But for those of you now only using digital, it's probably a little tricky. But if we start at 0 and go up, that is going to be angles measured in positive direction. You can also measure an angle in negative direction. I'll go over here on the not good degrees, but I can also measure, there's my initial side. I can start measuring this way for fun, but that would be a negative direction. We tell people we're going in the negative direction. So that's more than -90. That's like -120 or something like that, right? So this is about, let's do about -120 degrees. There you go. So you got that. We got this thing called bearings. They work differently, and that'll mess your heads up completely, but it's always worth a little fun. What else could we talk about? Let's talk about, my favorite reference angle. We're going to need this one. This one's super valuable. That's why it's highlighted. That's why I put a little star and a smiley face after it. Reference angles are the angle between the terminal side. What's the terminal side? And the x-axis. So the angle, and it's the acute angle, the smaller angle, right? Acute, less than 90. Now I'm going to make an exception for the first one, but acute, less than 90. Make sure that is called your reference angle. Now I want you guys to try these. So if you want, you can pause the video, or you can go ahead and join me, but we want to draw these angles. So I'm going to draw a little graph here. And what I want to do is draw pi over 2. So remember, this is 0, or 2 pi. Then, so if you cut that in half, that's pi. And if you cut that in half, that's half a pi. And that's 1.5 pi's, or 3 pi over 2, whichever way you want to put it. And now I got to graph pi over 2. Where is that? Well, that's a piece of cake. That was one of the angles right there, straight up. So initial side starts at 0, terminal side starts at a half, there goes to a half pi, and there is my angle drawn. So I drew the radian angle, and the reference angle, okay, so which way is the acute angle? Here's the terminal side, right? This is where it stopped at, right here. This is my terminal side. How many radians, or degrees if you want, is it back to the x-axis? Well, it would be 90, right, on either side. So either way would get you back to the x-axis, and they're exactly the same. Usually you'll calculate one, and then the other one will be smaller, and you'll take the smaller one. It should always be less than 90, but I would say our reference angle is pi over 2. And that's going to come in handy a lot later, but right now, I just want you to get used to thinking about it. All right, let's try 11 pi over 6. A lot of kids hate radians because they have no idea where 11 pi over 6 is. Don't blame them, right? So what could I tell you? I could tell you that this is 0 and this is 2 pi. Well, that's not going to help me in sixes, right? Like I even know, let me get this guy out of the way now. I even know that this is 1 pi. But instead of calling it 1 pi, I'm going to call it 6/6, right? So instead of calling this 2 pi, I'm going to call this 12/6. Why would I pick 6? Because look at the denominator. It was 6, right? So I got that. Now, right in between 0 and 6/6 would be 3/6. Hence pi over 2. And down here between 6 and 12, just add those two together, there you get 9/6. All right, so there you go. There is the angles, or all the measures of the angles that I know, the quadrantal angles we call them, on the x-axis and y-axis. And I want to find out where 11/6 is. Well, guess what? It's just shy of 12/6. So here's the initial side. And if I'm measuring around this way, I would stop about there, and there's maybe a little closer, but that's good enough. This is 11/6 of a pi, and there she is. Now, what is the reference angle? Remember, the reference angle is get me back to the x-axis. So is it this angle? Call that A, or is it this angle? We call that B. X-axis, not y-axis. Don't be that kid that does the y-axis. All right, get me back to the x-axis, and let's see. That it looks like it'd be angle A, I hope you're saying. How many radians is angle A? Well, angle A gets to 12/6, and we're at 11/6. So I guess the reference angle, why did I put triangle before? That's weird. Reference angle is 1/6 or pi over 6. That would be your reference angle. Yeah, let's change that to an angle. And there you go. See how nice and easy? Now try doing the next one. Do 4/3, right? Do 4/3. Actually, how about we pause right here? Let me ask you 4/3, and I'll be right back. All right, nice work on that one. Now let's see how you did on it, right? 4 pi over 3, so I'm going to call this 0, and I'm going to call this pi, 1 pi. Oh wait, we're going to do thirds because the denominator was 3, so that's 3/3, which means this is 6/3, and what's right in between 3 and 6? How about 4.5 thirds? And between 0 and 1 is 1.5, but I don't really need that, but I'll label it anyway. So there's my labels for this, and if you didn't want the decimal in there, definitely clean it up to make it, 3/6, so pi over 2. But I want thirds because I want to know where 4 pi over 3 is, and I can tell you that that is somewhere between 3 pi over 3 and 4/5 pi over 3. In fact, it's closer to the 4/5. So here is my angle, and remember we're measuring it this way, and so therefore that is 4 pi over 3. I know exactly where it is. Now, what is my reference angle? Well, it's this guy right here. It's not this long way. That's no good. So it's this shorter way. And what's the difference between 4 pi over 3 and 3 pi over 3? Well, that would be exactly pi over 3. So the reference angle is pi over 3. All right. What about D? D gets it a little crazy. We're 2.9. 2.9 what, right? There's no pi, there's nothing. So you got to realize that pi is just a number. We all know pi is about 3.14159. And so you want to make sure that it goes on forever, but you want to make sure that you know where that is. So again, this is 0, and this is pi over here. So this is 3.14159-ish. And then that means this is 6.28-ish. And then right in between 0 and 3.4 is 1.57-ish. And then if you add those together, is that 4.6, 4.71-ish, I guess. Check my math there. But ish, right? Now, if I want to know where is 2.9, well, I can tell you it's between 1.5 and 3.14, so I'm going to put it out here. It is right there. There it is. And remember, I was measuring this way in the positive direction. I should have done some in the negative direction, but I didn't. 2.9. And what is my reference angle there? Well, whatever the difference between 2.9 is and 3.14. So what is that? 0.24. So the reference angle is about 0.2, what did I say? 0.24159-ish. All right, notice I use squiggly equal signs. That means approximately equal to. It means I'm not giving you the exact answer. I'm just giving you an approximate answer. No, you can't do that on a test for every answer, but if it's an approximate answer, yes, you should. If you know what it's equal to, then definitely use an equals sign. All right. How do you convert from radians to degrees? There's a simple formula. I call it dimensional analysis, stoichiometry, whatever you want to call it. They're all beautiful names, but here we go. I'm going to take 200 degrees. Right? Now I'm going to multiply that by, and this is a very handy thing that you learn in chemistry and you learn in math, and it's just dimensional analysis, meaning change the dimensions or analyze the dimensions or units or whatever. Unit conversion would be another nice word. I'm going to multiply that by a fraction, right? And I'm going to make sure I put degrees on the bottom, and I'm going to put radians on the top. And all I need to do is multiply this by a fraction that represents the number 1, because multiplying by 1 wouldn't change it any, but somehow relates degrees and radians, and pick anything you want. I know 0 degrees and 0 radians. Well, that would be a bad one, because multiplying by 0 is not multiplying by 1. So I can't do that. What about 360 degrees is 2 pi? A lot of people will do that. So they'll type that in, or I'll just do a little smaller. I'll do 1 pi is 180 degrees, right? So that's my conversion, and the conversion you see up above. And so the reason that works now is, all right, got dropped off a little bit there, but to let you know, the reason that works is because pi radians in 180 degrees is just like multiplying by 1. It's the exact same thing. So how do I clean this up? Well, I get 200, oh, I don't want to be in highlighter. I get 200 pi radians, and then the degrees canceled over 180. And then you can clean that up a little bit, like 0 can cancel 0, so that's 20 over 18, which now is what, 10 over 9? So how about 10/9 pi radians? That's what 200 degrees is in math. So now you guys can convert any degree into something useful called a radian, and we will be able to use it. Now, what if for some reason you just won't let go of degrees? I mean, and then so I tell you, graph 7 pi over 8, instead of being that kid that's like, oh, that's 8 eighths right there, so 7 eighths is right here. You're like, no, I want to figure out where it is. Fine, convert it to degrees. I don't know why you would, because that's just weird, but whatever. And so radians, so what am I going to do? I'm going to multiply that by, again, I want radians on the bottom this time because I want the radians to cancel, which means degrees go on top. And you can do this with anything like feet and inches and miles and whatever, right? As long as those two things are equivalent, it's cool. Now, again, I know that 180 degrees is pi radians, and notice what happens. Radians cancel radians, pi cancels pi. I think 8 goes into 180. I don't know, but I know if I cut them both in half, it's 4 and 90. I can cut them both in half again, 2 and 45, and I think that's it. So this is 7 times 45. What is that? 7 times 40 is 280, and 7 times 5 is 35. So is that 3, 8, 9, 10, 11, 315 over 2, 315 over 2 degrees. And there you go, little degree symbol. By the way, if you don't put the degree symbol, I'm always going to assume it's radians, and I want you to do the same thing. If you see something that is written that is an angle, then there's no degrees, then just assume it's radians, because who the heck's going to use degrees anyway? Nobody, right? All right, this thing's getting a little long, and I'm going to have to speed it up. So maybe I'm just going to point this out. This is a cool formula right here. Remember arc length? So you have a circle and you have an angle here in the center, right? And you know this angle because you measured it. And you want to know how long this arc is right here, right? That whole thing. Super simple formula. It's S equals R theta. What does that mean? S is the arc length. That's the arc. R is, of course, the radius measured however. But theta has to be radians. It has to be radians. It has to be radians. It has to be, say that, it has to be radians, because again, degrees are worthless. So this formula won't work in degrees. You'd have to convert your degree to a radian first, and that's what you would do in part B. Part A, though, simple as could be. I literally am going to take the radius, which is 4, and the radians, which is 5 pi over 6, and I'm going to multiply that together, and I'm going to get 20 pi over 6, which is really 10 pi over 3. But what units is that? That's in centimeters, and because it was in centimeters. Make sure you remember your units. Units are important. Over here, just remember that you want to convert that must be in radians. So you can ask me this one in class. I'll probably now throw them on warm-up or something like that. Must be in radians. There's one to convert to degrees. Again, that's a nice conversion. That's it. We'll have to talk about this in class, because I don't want this video to be too long. So I will see you tomorrow. Stay happy.